So the PDCP entity, when it is created as a software, it works along with RLC operating in either UM mode or RLC operating in AM mode. That is what this picture tells us. So that also gives us another hint that PDCP works only in the RRC connected state. It won't be working in RRC idle mode. Reason, if you remember the last slide that we have studied, I already explained what are possible only in RRC connected state, not possible in idle state. Because you have a configuration for that, G node base RRC and mobiles RRC need to communicate with one another. So PDCP also works only with RLC UM mode entity and AM mode entity. That means after RRC connection is established. Obvious. So what happens before RRC connection is established? PDCP doesn't exist. That means we don't need PDCP protocol layer services when the mobile is in idle mode. It is kind of absent from the whole story. So in the layers, data, whatever the kind of data that you can exchange in the idle mode, it is kind of direct. For example, if it is moving from RRC, it directly goes from RRC to RLC, RLC to MAC, MAC to physical layer. Because we are not involving PDCP there in the idle mode, as it is not capable of doing any work in idle mode. Or in another way of explaining it, whatever the functionality that the PDCP achieves is not needed in idle mode. PDCP also, just like RLC, be configured by RRC. It only works with the radio bearers that are mapped onto DCCH and DTCH, even if we ignore other ones. The other things we are ignoring, multicasting traffic channel, side link control channel, side link traffic channel, we are ignoring them. So we are not learning that part. DCCH and DTCH, that means only for either RRC signaling messages or traffic here. Now, how many PDCP entities exist? That is kind of dependent on one factor or a parameter called as uh, radio bearer, RB. So each radio bearer is associated with one PDCP entity always. So how many radio bearers we have? That many number of PDCPs we operate. That many number of PDCP software instances we create. It depends on the radio bearer. So that means whatever the PDCP work we do, we kind of giving a name to it called as radio bearer. Of course, only PDCP won't be involved in that radio bearer concept. The other layers also will have their own role to play, which we will study overall what happens as a radio bearer at a later point in time. But just to see the relationship, it's one-on-one relationship. One radio bearer is equal to one PDCP. And this rule is not applicable for SRB0 because this one special radio bearer called as SRB0 only when it as we discussed before RRC connection are in idle mode, no existence for PDCP. How many RLC entities PDCP deals with? In normal cell configurations, single cell configurations, your PDCP either deals with one UMRLC entity for uplink, one for downlink, because uplink and downlink entities would be considered separate. One for each direction. Direction here is uplink and downlink. In case of AMRLC, it is a single entity because we have a coordinating entity. It is working together, sending part and receiving part together. So PDCP also links with one entity. But because two RLC entities are there, you should not imagine that they are two completely separated RLC entities. They are operating for same PDCP itself, but one for each direction. That's it. Now we have the concept of split bearer, PDC bit duplication, dual access protocol stack bearers, etc., where mobile is entitled to use the services of multiple cells. So mobile can run it on two NR cells, one NR cell and one UMT, one LTE cell. Like that, you can perform the configurations in any of these things. In such cases, what happens? Number of RLCs would basically increase in these cases. So, for example, if you take split bearer, where the traffic would be split, half the traffic would be sent through one cell, half the traffic would be sent through another cell. PDCP generates all the traffic, but you have RLC and below, we have two entities present, one in each cell, if mobile is dealing with two cells. So traffic kind of split. So PDCP, if it generates 10 PDUs, 5 PDUs it sent through the first RLC through first cell, and another 5 PDUs it can send through second RLC through second cell. That is possible in split bearer kind of scenarios. Or for providing reliability, instead of splitting, we can kind of duplicate them. All the 10 things we can send through first cell as well as second cell for providing more reliability without missing the things. Either if you miss in the first cell, you would receive it in the second cell, or vice versa. But because we are not studying much of these dual scenarios, all this, as it is completely, selectively excluded from your course, I'm not going into these details of having multiple cells. But anyway, once we learn the normal concept, working on top of that and getting to understand the remaining thing is very easy. So once there is a requirement for you to develop any of the PDCP related software at a later point in time related to this, you can easily build on top of the knowledge that we are going to have for normal configuration. So for the rest of the spec, we would be basically referring to this normal cell configuration where either PDCP is going to be associated with a UM entity or AM entity. The UM entity, transmit and resumption are separate. UAM, it is combined. Okay, so what are the jobs that PDCP performs? Just like how RLC does, PDCP also does some duties. What jobs it performs? So here is the big long list of them. On the left-hand side, you see the transmitting PDCP entity. On the right-hand side, you see receiving PDCP entity. And we have to kind of study this functionality one by one. So the first one. So if you take a look at this arrow, if you recognize the colors, this color is right now representing RRC in our presentations. This is kind of representing a protocol called as SDAP. So signaling data comes from RRC protocol and user data comes from SDAP protocol. So that arrow is representing that. Now we have the functionalities. So PDCP has got its own transmission buffer and adding a sequence number for the packets, its own sequence number for the PDCP PDU that it prepares. And then we kind of wonder why RLC is already doing that stuff, numbering the things. Why PDCP also have to take care of it? You remember, I have actually introduced one problem in RLC which I did not completely cover it up. I told that it might be done in PDCP. So right now, again, I am not covering it completely, but I'm linking that point here. So the sequence number has got something to do with that particular process that we have discussed earlier related to the SDUs and SDU segments, especially configurations. So we discuss more about it related to that sequence number later. What are the other activities uh, that PDCP performs? It does header compression and decompression, or data compression and decompression. On the sending side, it performs, on the transmitting entity, it performs compression. On the receiving entity, it kind of performs decompression. First of all, what is the meaning of compression, decompression? Compression of something. For example, if you take uh, a file, big file. If you compress it, the advantage is that when you have to attach it to a mail, you have to use less bandwidth to transfer it, and it can be sent faster as well because it is compressed. It is converted into a zip file kind of stuff. So compression always will help you to reduce the operational bandwidth. So PDCP is kind of a radio processing protocol, which obviously need to help the radio conditions. One of the tasks that they allocated to PDCP is to do these compressions of higher layer things so that you can achieve that bandwidth efficiency. Of course, time would be wasted. On the sending entity, compression takes some time. On the receiving entity, decompression takes some time. But you achieve the radio spectral efficiency. One of the important things that they always consider. Okay, now after that activity, you kind of performing integrity protection. Uh, what's the meaning of integrity protection? The opposite task on the receiving entity is called as integrity verification. You have to protect each and every piece of data that you send to PDCP with some kind of a special code. With the help of that special code, the receiving entity can kind of validate whether the actual received packet is sent by the actual sender or some third party attacker is sending it, like by acting like the actual sender. We wanted to kind of detect that. So that mechanism is called as integrity protection and integrity verification. Protection happens on the sending side by attaching some special code. On the receiving side, that would be validated so that you come to a conclusion that there is no attacker in the middle who is trying to send some information to G node B, just like acting like a mobile phone. You kind of wanted to make sure that we call it as man in the middle or intruder attacks. Protecting the system's integrity. Okay, next. Ciphering. Converting the data into a secret format. That is what we call as ciphering, into encrypted format, which can be decrypted only by the other PDCP system component, which have got the required codes to do it, required secret codes to do it. Again, the middleman who wanted to attack, not only they will try to generate some data and fool the other guys, but they'll also try to sniff what is going on the radio interface. They will kind of capture it, and by using a perfect device, they can remove all the headers like RLC header, MAC header, etc. That's very easy because those specifications are public specifications. Anybody can kind of write the software to delete those headers by processing it with the software. But you don't want your higher layer data to be compromised. So at PDCP level, we cipher the data, encrypt it, so that there it will be much more protection for the data that we are transmitting on the air. And it adds the corresponding header, PDCP header based on the functionality it is performing, and then it sends out. But while it is sending out, there is this block called as routing and duplication. We kind of ignore that. Reason, that is required only in case of duplicate PDCP duplication and the other things that I have introduced, like ENDC cases or NRDC cases, whatever the scenarios where you are trying to send the PDCP packets through multiple cells, multi-cell scenarios. In such cases, for example, if you have decided to send PDCP packet through two cells for providing extra protection, extra reliability, one we call it as master cell group and the other one we call it as secondary cell group related cells. So you send one copy on your cell and you send one duplicate copy, you route it to the SCG cell. From there, it would be dispatched to the mobile. Of course, mobile is some kind of a device which is capable of receiving from both the cells at the same time by using two stacks, which called as the DAPS, dual active protocol stack. And it would receive it, process that, and you know deal with it. But it can be duplicated. But of course, you have to rectify the duplicate. You have to take, if one of the thing is missing, you take the one that is received successfully. Both are received, you throw one and you take one. If both are successfully received, a kind of activity. But right now we are going to ignore this a little bit, routing and duplication part. Now, what is this bracket saying here? Packets associated with the PDCP SDU, packets not associated with the PDCP SDU. First of all, what is the meaning of a PDCP SDU? We all know anything that comes from the higher layer is called as the SDU. So the anything that comes from the higher layer goes through these processes. That is what is the meaning. But the packets that are not associated with the SDU, typically they may not be, uh, you know, having all these processes. Instead, they will directly start with adding the PDCP header itself directly without having these processes. That is what this typically represent. Can anyone tell me what are the packets that are not associated with the SDU are called as? What they are called as? A question. I want three answers before moving forward. Come on, guys. You guys are not asking questions anyway. Answer my questions at least. Simple question. What are those packets called as? Transparent packets, wrong. Signaling messages, wrong. Signaling message also is SDU. I already draw the arrow here and I clearly told you. So this is RRC PDU, which is also called as SDU. This is SDAP PDU, which is also SDU for you. Anything that's come from the higher layer is SDU. I'm telling you. So this is SDAP PDU, or from PDCP point of view, SDU. This is RRC PDU. From PDCP point of view, it is SDU. My question: what are the things that are not associated with SDU? Somebody told non-access. That is also wrong. Non-access signaling means NAS messages. NAS messages would be there on top of RRC. If NAS is packed inside RRC, RRC PDU comes to the PDCP. That will be considered as SDU because NAS is anyway coming through RRC, even though it's not directly dealing with PDCP, but it comes through RRC. So that answer is also wrong. This thing I have explained you, not one time, maybe I think I guess 10 times throughout your lectures. So you have to basically go to the point where I have explained you. Exactly. One answer I got. That's good. Jeevaratnam. Answer is any control messages of PDCP. I told you all these L2 protocols will have their own control mechanism. So you have RLC level control PDUs, which are called as the status PDUs. And we have seen MAC level control information, which we called as control elements, named as. At PDCP level also, we have control information, which is not coming from the higher layer, generated by PDCP for the sake of PDCP, for the sake of other PDCP. The other PDCP reads it, understands, acts upon it, but won't need to send it to higher layer. Whatever we receive from the higher layer, we need to dispatch it to the higher layer on the receiving entity. You don't have a choice. But if anything that is generated at the PDCP level itself, it need to be sent only up to PDCP. That's it. After that, PDCP reads it. PDCP makes a decision what to do with it. But PDCP won't send it to the higher layer. No. That's the point. Okay, great. Finally, we got answer one question. Reception buffer. So we got the uh, integrity verification done. So all opposite tasks: ciphering, deciphering, integrity protection, integrity verification. If adding the PDCP headers, we are removing it. You are doing the compression. Here we are performing decompression. And if any of the if you are duplicating here, so after decompressing and everything is completed, you detect the duplicates and you discard those duplicates if they are coming out of order. Or if required, you perform the reordering. If their order is changed with the help of the sequence number, you can identify the correct ordering. And then after completing all the tasks, you send the data to higher layer. But why exactly is these units in the order that they are? First of all, how do they do these tasks? Why this order matters? We'll find out. So there is definitely logic behind it. But this is in case of normal scenarios where we are dealing with only a single RLC entity. But when you are having multiple RLC entities, in case of duplications or ENDC cases or NRDC cases, whatever, the situation will be multifolded. So after receiving the data, you add the sequence number, you compress it separately for two different RLC mechanisms. You add the integrity protection separately, ciphering done separately by using different ciphering keys, corresponding header, and then you send it out. Like multiple things, separate processing mechanism for each one. Because this is kind of present in the specification, I have to present it. I presented it to you, but we won't study any further on it. It is not part of our curriculum. You're ignoring it, the split bearer related stuff. Okay. Now, whatever the functionalities that the um, PDCP is performing, we kind of divided them into three major categories: compression, decompression, security mechanisms, and data transfer and management. I myself have categorized this into three categories. This is not present in the spec. Sometimes I deviate from the spec. I myself have categorized. If you go to the specification, you won't see this. So for myself to explain it easily to you. So we are going to see these things section by section. So first we see the compression decompression related activities. So what and all the different compressions that PDCP can perform? So there are three different kinds of compressions that the PDCP can perform, or it is designed to perform, 5GNR PDCP. First one is called as header compression by using an algorithm called as ROHC algorithm or robust header compression algorithm. The second one is header compression and decompression by using EHC algorithm, stands for Ethernet header compression and decompression. And the third one is uplink data compression and decompression by using UDC protocol, user data compression protocol or user data compression algorithm. All these are done by mathematical algorithms. All these steps are done by either ROHC or EHC or UDC. Now, what are these header compressions? Why do we need them? Or first of all, what is these total compression types? And why do we require them? We have to see each and every case separately, one after the other. We again have to visit this slide once again to see it as a summary after completing everything up. So now we take up the first one, even without any further explanation. So we are going into the ROHC part, stands for robust header compression. You can see First two letters here, H and C have taken, they have named that algorithm after that, ROHC. So what is this ROHC algorithm? Why do we need it? To understand that, we take what is happening on your mobile equipment. Now, if you take a look at here, we have application, presentation, session, transport, and network. Let us suppose that these are all the things that are present in your mobile device. And mobile's applications are kind of generating the data, and they will be processed, and we'll be adding all these protocol headers one by one. First, application generates the data for which each protocol layer would be attaching a header. We know that presentation, session, transport, network, every layer would attach their own specific headers. Now, we also know that this network layer packet that is generated in your mobile phone is typically the one we call it as a IP packet. We simply be calling it as IP packet, or your actual user data that you need to transport. But these are our general protocol stack that is present in your computer or in your mobile phone till the IP packets are generated. All the layers will be adding their respective headers. But then we have our radio protocol stack below this, because your IP packet need to be processed by the radio protocol stack. We learned that. So we have SDP, SDAP, PDCP, RLC, MAC, and physical layer. So each of these layers also will attach their respective headers. Of course, physical layer won't attach. We can't consider that as a header on the physical layer side, because even though it attaches the CRC coded bits, etc., it will juggle the data. It will perform the scrambling and various other things. So if the physical layer part, whatever that is added, won't be staying at the starting. It kind of get mixed everything. It kind of clubs that. That's why I've put one circle around it. But PDCP also adds something. Sorry, your physical layer also adds something like CRCs and coded bits and so on. Now, this is the normal scenario. Look at how many headers have been added for the original data. Presentation session transport network for generating IP packets. After that, our radio protocol stack headers, SDAP, PDCP, RLC, MAC. So far, we have learned about what does physical do, what does MAC do, what MAC header MAC adds, what header RLC adds. And today we are going to learn about PDCP also. SDAP we'll see later. But the other things we already know. First class we have studied what header presentation adds and session transport network, the IP headers and TCP headers, SCTP headers, etc. That part. Each protocol layer adds the header to do their own functionality. We got that clarity. Typically, when the applications have originated the traffic, this application data can be maybe compressed by the application itself. It may be compressed. Because the data part is already compressed, that is in the best fit situation to send it without wasting any bandwidth. But the problem is with these additional headers that are being added by every protocol layer. These protocol layers especially, they might add up a lot of header, these protocol layers that we have. For example, network layer may add 20 bytes of header for every IP packet. Transport layer, if it is operating on TCP, it also adds 20 bytes of header. Session layer kind of adds 12 to 20 bytes of header for different situations. Like that, every protocol layer would be adding the headers. They thought that, hey, we are already compressing the data. There is not much scope to compress it anymore. If at all we wanted to make this whole IP packet that is already arrived compact, to make it to a smaller size in order to improve our radio conditions or increase the radio spectral efficiency, it is better to implement this mechanism, this um, compression on these headers. We may try to compress these headers, even though they are of very small size, 20 bytes, 20 bytes, 12 bytes, etc. But if you can save even that, that is good. Because for every IP packet, you are saving that much, 20, 20, 12, like that. For every IP packet, you would be generating, a mobile equipment would be generating hundreds of IP packets or receiving hundreds of IP packets per second or minute. So you would be saving a lot overall. If you can even save these, save, compress these headers instead of sending them as it is. Now the question is, so we understood that because the data is already compressed, only the headers are kind of giving us a scope to compress themselves. So we can kind of compress these headers. So that is the target of the PDCP protocol, to compress these headers: network layer header, transport layer header, session layer header, and presentation layer header. Because that's the only scope left out, as the data is already compressed. So how do you compress this headers? Or how do you compress it? We'll find out that a little later. But what happens after the compression works out? If really compression works out, what happens? Let us see some examples for it. First example, you have your voice data that is getting generated from your voice application, which is using no presentation protocol layer. So presentation layer is kind of absent. It is not adding any header. At session level, we are using RTP protocol, and at transport level, we are using UDP, and that voice packet is packed into IP. Let us take that it's a VoIP packet, voice or IP packet. So RTP added the header. RTP header is like 12 bytes. UDP adds the header, which is 8 bytes. IP adds the header, which is minimum 20 bytes. So after all these guys added the header, we kind of say 12 plus 8, 20 plus 20, 40 bytes header got added here, totally, these three layers together. Now our target is, by using ROHC algorithm that is running, that is being hosted at the PDCP level, we wanted to kind of remove these headers and replace them with an intelligent ROHC header, which is typically very small. For example, if the size of all these headers together is 40 bytes, even if we are attaching the ROHC header, robust header compression header, or the compressed form of this header, will be typically 3 to 4 bytes. That's it. Even if we have to send it 3 to 4 bytes, we're replacing it. Oh, now you ask me the next question. Hey, ma'am, in this IP packet, the source IP address is mobile phone, destination IP address is application server to whom you are sending this VoIP packet. Now, if you remove those IP headers and replace it with the ROHC header, which is somehow compressing it with 3, 4 bytes, how can we send this IP packet to the destination? Maybe we are compressing it on the mobile phone. After this is received at Gnode B, Gnode B need to forward this data to a VoIP server, which is present somewhere else in the world. Now, without IP addresses, how can we forward it? Can we forward it with the ROHC header? No, we cannot. So what need to be done by the Gnode B? Before forwarding this total data packet that is received, IP packet, the Gnode B need to reconstruct the header once again, reconstruct the RTP header, reconstruct the UDP header, reconstruct the IP header. It need to reconstruct. It cannot send it as it is with the ROHC header itself. What is that we are gaining? While it is on the while it is on the transmission path on the radio interface, air interface, the size is getting reduced. Instead of having this RTP, UDP, IP size to be totally um, 40 bytes, we are replacing it with an intelligent ROHC header. What does this ROHC header do? It is an intelligent mathematical algorithm that will kind of analyze these headers and kind of finds the ways to compress those headers, make it into minimalistic size. How it does that, we will find out. But it does that, capable of that. And the receiving system also, if G is compressing it, mobile will have the mechanisms to decompress it, because mobile also have this ROA protocol software running in its PDCP level, PDCP software level. Same thing with um, in the reverse direction as well. If mobile does the compression by removing these headers and replace it with ROHC information, the receiving entity will be able to reconstruct, or we call it as decompression. Now, if RTP, UDP, and IP headers are present in your IP packet that is getting generated, before the radio protocol layers are doing their duties, these ROHC algorithm have to compress these headers and make it so that you will be able to use lesser bandwidth or lesser radio resources and while transmitting your data. You remember, we called PDCP, RLC, and MAC layer are radio processing layers, which are kind of helping the radio situation. They are doing the duties to help deal with the radio scenarios. So PDCP is doing its own duty. Now, what if the data that is originated not having RTP, UDP, IP protocol headers, but something else? If it is not a voice payload, if it is just a UDP IP payload application, you don't have presentation session, you have only UDP header and IP header added. Presentation and session are ignored. If you remember our TCP IP protocol stack, I told you that number of protocol layers are not needed to be constant. They can be like, uh, they can be, you can miss some of the protocol layers if you want. So in this case, application have chosen not to use presentation services and session services. So it's having only trans. You kind of use UDP IP. So whatever the protocol stack headers that are getting added in your higher layers, ROHE should target to reduce those header sizes and make them compact so that you will be able to use less bandwidth in your radio interface. For example, if application data is directly packed into IP, very rare situations, but even in that case, ROHC need to work towards compressing only IP header. Or we are having a protocol called as encapsulating security protocol, ESP, which is also called as IP security protocol, which works at the same level layer as the IP. It is called a 3.5 layer protocol, this ESP. So if your application data is packed into IP security packet and IP header, now ROHC work towards compressing this ESP IP headers. The other three layers might not be there. Presentation, session, and transport layers. Directly, it is being packed into this. So ultimately, ROHC is an intelligent software algorithm which can target to compress any kind of higher layer headers that are getting added in various different situations, depending on what kind of traffic you are sending and what kind of a compression you have to perform. Now, Who tells ROHC that whatever the data that we are getting from the higher layer is containing what kind of headers? PDCP kind of not required to guess that. It is going to be configured by again RRC in the form of this particular table. So if RRC comes and tells the PDCP that, hey, I'm configuring a profile identifier 002 for you, immediately the PDCP protocol understands that, okay, the higher layer data is going to come to us with UDP IP headers. So we have to make this ROHC software, ROHC algorithm work to reduce the UDP IP size, UDP IP header size. PDCP understands that. So that means the RRC, which is doing this configuration, somehow must be aware of what headers are going to uh, come from the application layers when the user data is arriving. On the basis of it, this configuration can work out. Now, you may say, hey, UDP IP, we have one here, one here. What is the difference between them? Now, this is kind of by using some old specifications, 3095 and 4815. This is kind of latest one, 5225. Now, the latest one can do more compression when you compare with the old ones, because this is updated software, updated logic, because humans do keep learning and evolving. They keep kind of developing the things always. So already one existing method is there. They found out a better method to do the compression, to increase the uh, compression rate much more. But now, which one will be configured out of the two? It will be clearly indicated by RRC, either two or one or two. But first of all, mobile, at the time when it is communicating with the Genode B for the first time, as I told you earlier, it kind of convey something called as capability information, UE capability details. As part of this capability information, mobile clearly explains to Genode B, hey, I support algorithm 3095 and 4815 based compression mechanisms. I don't support 5225 based UDP IP compression. That's kind of software is not present in my mobile phone. So I'm not a latest device, old device. When you tell this to the network or your Genode B, Genome kind of understands and it will never wrongly configure. It will say that, oh, if that is the case, then the profile identifier I should configure is only for two. That means even though it is UDP IP header, instead of using the latest technique, you have to use old technique. But still it can do some compression instead of nothing, something is better. So for different protocols, there are multiple options. Some protocols have got only one option. But ultimately you have options available. But if RRC comes and tells the PDCP that profile identifier is 0, that means PDCP doesn't require to perform uh, the compression, no compression. You're just kind of ignoring it. But now we worry about all this compression is good. We thought that the compression algorithm would do this stuff and somehow remove the higher layer protocol headers and compress them into small size. But how it is done? How exactly it works out? For doing that, we do a small practical, which gives us some kind of an hint about it. And on the basis of it, we can understand this concept. I'm using Wireshark. I hope all of you can see it. I'm using a tool, Wireshark, which is used for capturing live traffic. Right now, whatever I'm speaking and whatever I'm presenting, all of you that you are getting uh, it to the internet. Right now, I can use this Wireshark and capture the traffic that is going in into the internet. So on this Ethernet interface, I'm capturing the traffic, as you can see over here. I've captured it for some time and I'm stopping it now. I've stopped it. After stopping it, I kind of wanted to show you these packets one by one and wanted to ask you a question on that. So please observe what is going on. So there is one IP packet here, next IP packet, next IP packet, next one, next one, next one. All these are continuous IP packets that are coming in from server to my computer. My computer's IP address is 10.0.10.2. This is the server's Google GoToMeeting server's IP address. From that, I'm getting some information, some data. But what am I going to do? I'm going to open these headers and show you these headers. First, I'm opening the UDP header. I hope you can see the header. Everybody can see the header fields, small or okay?
Okay, sir.
Okay. Now look at this. Now there is a UDP packet here. There are some header fields and their values present. Now when I click on continuous packets, you have to tell me like what is the thing that you are observing when I kind of click on these things. So you first we see the source port number 1853, destination port number 49,878, length 1057. There is a checksum. These are the four fields that we have in UDP. If I click on the next one, now you can observe the source port number and the destination port number remain same, isn't it? But is there anything else that you are observing other than that? Anyone?
Length has changed, sir.
Yeah. Length is changed. Checksum also has been changed. If you take continuous IP packets, normally speaking, only a few fields are getting changed, as you can observe in this particular header portion. Similarly, if you take IP packet level headers, if you take continuous IP packets, you see these many header fields are there. Version 4, 20 bytes, differentiated service field is 0, total length 1077, identification, flags, time to live, UDP, source address, destination address, and so on. Now, if I click on this and if I click on the next packet, now you observe that only 2 or 3 fields have been modified from that. So total length is changing and identification is changing, checksum is changing. Rest of the fields header values are remaining same, except those 3 things that are changing at the IP level. Similarly, if you take any TCP packets, not only UDP, if you kind of take TCP packets, continuous TCP packets that are flowing in one direction, and if you observe them, even TCP header, if we open it and see what's going on in the TCP header, so these are the TCP header fields, port number, all these things. You don't need to read those parameter values, but when you click on it, you will automatically know which ones are changing because that is where our eyes go. Acknowledgement number is changing. And, yeah, that looks like it. Checksum is changing. Checksum and acknowledgement number. Other than that, nothing else is changing. Rest of the field values are the same. So can anyone tell me, why did I show you this? What is this kind of giving you? What is the hint that is kind of giving you? Are you getting any hint here? Can you please tell me how this compression algorithm work? How this ROHC compression algorithm works? Anyone? Can anyone guess? Come on, guys. Two participations, please. Then I move forward. We have a lot of subject that need to cover fast. No idea? Okay. One answer we got. Good. So the idea behind this is pretty simple. Every time we are sending these IP headers, UDP headers, or TCP headers, the sending ROHC algorithm can kind of do the analysis on these fields and find out, hey, from the previous IP packet, in the previous IP packet, I have sent kind of all the headers I have sent earlier. But now I'm sending the first one. Now I'm sending the second IP packet, which is also containing IP header, TCP header, or IP header, UDP header, etc. But in these headers, lot of fields are kind of repeated from the previous itself. So now ROHC algorithm thinks that, hey, I can tell the receiving ROHC algorithm that I'm not sending all the fields. I'm kind of sending only the fields that are getting modified. You can send only that information to the receiving entity. You intelligently convey that to the receiving guy. Hey, I'm not sending you all the headers, man. In the previous packet, I have sent you all the headers. I'm only sending 5 fields which are getting modified in together, IP plus UDP headers together. 5 of them. Total fields are 20, but I'm sending you only 5. Those 5 which are getting modified. I'm sending you. Remaining 15, you please copy paste it from the previous values you have received from the previous packet. It can use that kind of knowledge. So basically, this compression decompression works on the basis of creating a kind of a coordination between the sending ROHC algorithm and receiving ROHC algorithm. They kind of creates that uh, a collaborating mechanism that works, and that goes multiple levels. So if you take a look at your data, if you have the voice payload, for that you have added RTP protocol header, like you have 12 bytes of RTP header, uh, 8 bytes of UDP header, and 20 bytes of IP header. So these different headers have been added. Now ROHC algorithm, after analyzing one or two, three RP packets which are continuously going, they will come to this conclusion after sending 2 or 3 IP packets containing all these headers in it. ROH algorithm come to a conclusion that, hey, all these fields, their values are not changing. They are kind of same. The IP version number is not changing. IP type of service is not changing because it is the voice packet. Every time the type of service is the same. Time to live value is the same. Protocol in IP packet, the protocol that is packed is UDP. The protocol number refers to 17, which represents UDP. So that protocol number is the same. Source address IP and destination address are not changing. Source IP address is mobile. Destination IP address is application server in the internet, or vice versa. So if it is downlink traffic, source IP address is application server, destination IP address is mobile. Even these two fields are also not changing. Each field size is 4 bytes, 32 bits. They are also not changing. Port numbers are not changing because port numbers identify which application is generating this traffic. That is not changing. Protocol type in RTP also is not changing. Synchronization source identifier is not changing in RTP, even though I'm not teaching you what is it. It basically represents how many different streams of data we are packing into RTP. If it is single stream, this number will be same every time. So after sending 1 or 2 packets, both sender and receiver can come to conclusion. I think sender thinks that I don't need to send these fields now. I can remove them. Receiver adds them from the previous values. Next level analysis. After 2 or 3 packets, sending ROHC algorithm and receiving ROHC algorithm come to one more conclusion. Some fields are changing, but some are more changing, but mostly fixed. For example, internet header length can be fixed, 20 bytes only. If IP header length is not changing, are these XCCM fields, whatever they are in RTP, they are kind of fixed fields. Fragmentation typically would be disabled for voice packets, and that also would be fixed. These flags would be dependent on the fragmentation. So if fragmentation is fixed, flags also would be normally fixed. Mostly fixed they are. Their possibility to vary, but in most of the cases, they would be fixed values. In most of the scenarios, like 99.9% scenarios. And that's also will be an added admin. We can remove even them. Now, some fields may have predictable values. They are changing, but they are predictable. For example, identification. IP packet identification is kind of works like this. If first IP packet ID is 5, second IP packet ID is 6, third IP packet ID is 7. Okay, now sender sent 3 packets containing this ID 5, 6, 7. Fourth packet, it will remove this field. Receiver understands that, oh, now I understood already the pattern 5, 6, 7. Every time it is incrementing by 1. First 2 times, sender will say that, sending ROHC algorithm say that +1. Instead of sending the entire value, you will simply send +1. To send +1, you require less size. Here, 2 levels of operation. First time, very first IP packet, you have to send everything. You have to send everything, full ID value. For example, ID value is 5,25,992. That value would be sent. Next value will be 5,22,993. Then one is incremented basically. So you don't need to send the entire value. You have to send just to the delta. To send the delta, you need very small space because you have to you have to simply tell +1. That's it. Which may require 1 or 2 bits, not more than that. You don't require 16 bits for that. If you need to send the entire identification, you require 16 bits. So there you are saving the space by sending only the information in 1 or 2 bits, the changing information, even though it is changing. Next time, what do you do? After you kind of come to a prediction that this identification is consistently changing, first it is 993, next it is 994, next it is 995, 996. Now I don't need to send it. I will remove it completely, kind of giving a hint to the receiver that this pattern is continuing. So receiving automatically will add 9 after 993, you add 994, 5, 6, 7, 8 without even you having to send the header field. So coming to the conclusion, basically this works on artificial intelligence. This is nothing but a small example for AI, artificial intelligence, where sending ROHC algorithm and receiving ROHC algorithm kind of analyze the ongoing situation, and they find out which fields are changing by what patterns, and can we predict the patterns, and if we predict it with those predictions, intelligent predictions, can we remove those headers, not sending them, so that still receiver would be able to reconstruct the headers even if we don't send that value, don't send that field value. There can be some fields which may be dynamically um, which may be dynamically changing. You may not even be able to predict those parts. You can't do anything with it. Dynamically changing parts, like for example, the total length and p might be dependent on the voice data. The black color ones are dependent on the white color part. If the voice payload is changing, the IP packet total length will change. At UDP level also, length field value will change, like that. So there can be some totally unpredictable fields. For that, you can't help. You have to send their values, or at least you have to send their delta values if they're having only delta change if every time. But ultimate goal for you is to kind of guess what's going on. So when it is working on these ROH, when it is working on ROHC algorithm, it is kind of have these 3 states. At initialization state, they kind of create something called as a context. The context is unavailable right now. What is the meaning of context? The initial set of values for the header fields that you are going to remove. If that is available, You will come to first order state once the context is available. So the compressor has analyzed, detected, and stored the static fields. And maybe it is sending only differences for the dynamic fields, not sending the static fields anymore. So the context has been already created between the sender, compressor, and decompressor. Typically compressed on the sending side, decompressed on the receiving side. But you can go one level next in the second order state where you are kind of, beginning to identify the patterns that are happening in the dynamic fields. So you can stop sending even the dynamic fields too. Of course, you can move around. Once you've gone to second order state, you kind of removing the dynamic order fields. But after that, after some time, the receiving entity came back to you and said that a decompression failed, man. Maybe I don't know, in the middle one packet might be missing or whatever. I couldn't do the decompression properly. Something wrong happened. I could not decompress. Now, when you say decompression did not happen, you have to go one step back. At least you have to send dynamic fields once that kind of a report is sent. If that also did not work, you have to go to the initialization state and you have to reset. You have to restart with all the header field values once again. You don't have a choice. You have to go back to the starting position. Now, this ROHC is a separate software that works in by sitting inside PDCP protocol. So we cannot say that this work is being done by PDCP. We simply say that this work is being hosted by PDCP. That's it. It is working on the instructions of PDCP, this ROHC algorithm. Of course, PDCP to set this ROHC things, it would be getting the instructions from RRC. It's all interlinking. So obviously, RRC is capable of setting this operation by telling the PDCP what is the profile that is getting coming to the play, and what are the number of maximum ROHC context sessions that that are coming up, and is it only uplink or uplink only ROHC or both directions it is working. Now, what is this continue ROHC context is? It is after your PDCP re-establishment takes place. If any time PDCP gets re-established, so that time you have to continue your ROHC operation from the previous step, or you have to reset it. During, for example, during handovers, if the PDCP also gets reset for some reason, or in case of radio link failures, if PDCP gets reset, will you restart the entire operation and send the fresh headers, or you continue from the previous place? That is what it is going to tell you. So only if it is supported, then it can be set. But it is told during reconfiguration whether you should continue the ROHC algorithm or you should reset it. So all these parameters are provided by RRC. What is this maximum number of contexts? Why this is needed? What is this maximum number of contexts, and what is the meaning of multiple contexts? Simple. A context is a set of header fields, header field values. Now, for this set of header field values, the compressor and decompressor kind of after analyzing, they found out that, hey, for the kind of data that the application is generating, there are two sets of patterns that are going on. One set of pattern is kind of doing, decrementing one particular parameter by 5. In another set of pattern, the same parameter is getting incremented by 2. Two different patterns are there. Now we create one separate context for each pattern. that is happening for the same set of header fields. So the advantage is that, with the help of that context that is in operation, you can identify like what values that you have to replace with. So you are allowed to create multiple contexts. Moreover, we are creating this ROHC operation. There will be one ROHC operation for one PDCP entity. One PDCP entity is associated with one radio bearer. But in 5G NR, one radio bearer can invite the data that is coming from multiple different applications with either same quality of service or with a different quality of service. But it can invite the data from multiple applications. If multiple applications are pumping the traffic into one radio bearer, each application would be using different port numbers and different IP addresses to destine those things to different application servers. So obviously, the IP address, the packets are coming to a single stream, to a single radio bearer, or to a single PDCP, or to single ROHC. But ROHC definitely sees that because there is two application specific data is getting merged here, getting combined here. The sending compressor and decompression algorithms have to create multiple contexts. They should not work on single context. As there are multiple this application generating some set of headers, this application generating another set of headers. You can't do the compression when you are sending mixed traffic, because if you compare two IP packets generated by two different applications, their header fields are completely different. Then that time your total compression algorithm will fail. But compression algorithms are not that dumb. They will be able to analyze it after two or three IP packets and say, oh, the data is coming from two different applications. So we have to create two contexts, two separate, you know, uh, yeah, header patterns. And we follow that. And this maximum number of contexts is kind of telling you how many parallel uh, contexts you can create. So more and more contexts you can create, more flexibility you will have. So you can implement much more higher level of artificial intelligence into it and create one context for every pattern so that you can achieve the maximum compression possibility for your headers. So NGRAN, so these are the UE capabilities, UE reporting its capabilities, like what it can support, whether this particular technology is supported or not, or what algorithms it supports. Boolean can be set to true or false. Uh, how many contexts I can create parallelly and so on. Now network will tell you during the configuration, NGRAN configures this ROHC at the time of setting up the radio bearer or at the time of creating the PDCP. Which ROHC algorithm you are going to use, and is the DRB continue ROHC is getting enabled or not. That means after the reconfiguration also, do you continue the ROHC operation or do you have to reset? How many maximum contexts you are allowed to use out of the supported ones? And the profile number. If it is uplink only ROHC, what is the profile number? If it is dual, then this profile, one of these profile numbers will be chosen. Difference between them is uplink only ROHC will only do compression only in uplink. That means only when mobile is transmitting the data, compression is required. When GNODB is transmitting it downlink, compression is not needed. You make this dynamic decision on the basis of live network conditions. In the downlink, if you have enough resources available, you don't require to compress because compressor wastes the time. So if you don't require, if you have enough resources, why do you need to compress the data or headers for that matter? You can send it as it is. You don't need to waste time on it. But uplink only you can enable it if you want. Only mobile sending in uplink because typically uplink resources would be lesser compared to downlink. As the network normally operators configure less resources for uplink, fight will be more. But for these, whenever you do this compression between the sending compressor and the receiving decompressor, Every time this, there should be a control packet coming back from the decompressor called as ROHC feedback packet, interspersed ROHC feedback. So it will come with the device bit. Device is also there in PDCP. Device would be set to 0, represents it is control PDU, because it is going between PDCP to PDCP. It is not carrying the higher layer data. And the PDU type would be set to 1. Sorry, PDU type would be set to 000. My mistake. 001, one only correct. Interspersed ROHC feedback, the PDU type there. So there are a lot of control packets. So the control packet that we are receiving for this particular operation is feedback. What happened to your previous ROHC operation? Successful or failed? You kind of get a report at least every now and then, not if not continuously. Based on it, the compression algorithm decides the next step. If it is a positive report, it continues the operation. It will keep removing the headers. But if it is a negative report, you kind of go for a reset. You once again send all the headers. Every now and then there could be a negative feedback and you have to send the entire headers once again. So you can achieve header compression all the time, always? No, you cannot. Every now and then it will go for a reset. That will be dependent on lot of conditions, radio conditions and what's happening and everything. And we don't need to study this ROHC feedback related information, as it is ROHC algorithm specific information. We are concentrating on only protocol level details. At PDCP level, the header is device PDU type, 4 reserved bits, which are kind of waste, sit with zeros. Feedback information that goes to the algorithm. When PDCP gets it, it delivers it to its own hosting algorithm, ROHC hosted algorithm. Okay, so this is the compression that is taking place for robust header compression done for network layer, transport layer, and session presentation layer related things, as you can see. So ROHC is replacing its own information in place of these headers. Depending on what protocol is working in higher layers. But it is not compressing our data, our application data. Only header compression is the duty of ROHC. So first part is finished. So your compression can work to do network layer header, network plus network layer security header, which is ESP header, or network layer plus transport, or network layer plus transport plus session. So these are the kind of patterns headed that ROHC can work to remove it. Now there are two more compressions, EHC and UDC. EHC stands for Ethernet header compression. Now you can ask me why Ethernet is coming into 5G. There is something called as a 5G private networks, where you are allowed to send application traffic by using Ethernet packets instead of IP packets, by using MAC addresses within the local network without having to go to the packet data network. In such scenarios, your traffic would be packed into Ethernet, and PDCP work towards compressing the Ethernet header instead of higher layer protocol headers. So your header would simply look like this. Normally, if a IP Ethernet packet is there, your application data comes in, and there is Ethernet header getting added additionally, because it's going kind of becoming local IP packet, which is going to be sent from one mobile to another mobile within the private 5G network. So at that time, you are allowed to perform. You can remove this Ethernet header. ETH stands for Ethernet header. Remove it and replace it with EHC header. That is Ethernet header compression algorithm, which also does this stuff the same way. So these are the Ethernet header fields. You have the preamble, our preamble and this preamble is different, guys, but concept is same. a delimiter, source MAC address, destination MAC address, and if it is, if it is having, what do you say, VLAN tag, then you have 802.1q tag that is present in your Ethernet header, type, length, field, and payload, and frame check sequence, which is nothing but CRC. Now, typically, your Ethernet compression algorithm will try to compress these headers. Mostly, these MAC addresses would be same if the traffic is going from the same device to same device in a private 5G network. So you kind of work to compress it. But now, the concept that you see here is application traffic can be directly be packed into Ethernet. That one option is available. That means there are, when no higher layers are involved, directly you are packing it into Ethernet. In that case, only EHC algorithm will be there working. Your Ethernet header compression algorithm would be compressing the headers. But if the application traffic is going through the higher layers and generating IP packet and then getting packed into Ethernet, that time we are going to have ROHC plus Ethernet header. ROHC compresses the higher layer headers. Ethernet header compression algorithm will compress Ethernet header. So they will do their respective jobs. Depending on your application traffic is getting directly packed into Ethernet or getting packed into IP and then Ethernet first, depending on what operation is going on in the net, based on the configuration of your private 5G network. But we don't care about that right now because this is not part of our curriculum, but I have to introduce the things related to PDCP. I'm at least teaching you this part. So I'm not going into the deeper details of this, like how this compression, decompression of the EHC work and so on. But from PDCP point of view, if the EHC is the operating algorithm to compress the Ethernet headers, now you have the interspersed EHC feedback packet that is sent at PDCP level. So you have the device is set to 0, represents control PDU. PDU type would be set to 010, which represents EHC feedback. So when there is EHC Ethernet header compression going on, you have to send Ethernet feedback, Ethernet header compression, decompression feedback. The decompressor will explain, okay, so far you have sent me 10 packets, and by compressing it, I have decoded everyone. I have decompressed everything based on the pattern matching and everything that we are following. No problem. You can keep compressing. No need to reset the context. Otherwise, feedback would be negative. You need to reset the context. But during the configuration, your RRC, when it is set, mobile equipment, first of all, need to report the EHC capability. It will explain the network whether it supports this EHC or not, which is a release 16 feature. And it also tells how many EHC parallel contexts it can have. And also it can tell whether it can support EHC plus ROHC together by joining them together, supported or not supported. It's optional parameter. If mobile is not included this, meaning is it is not supported. Mobile is reporting that it is not supported. Based on whatever is supported for the mobile, network is kind of going to configure this EHC algorithm on the basis of that. So it tells you how many parallel contexts that you can have, and is it only happening in downlink or is it happening in uplink also, and so on. The things like that will be configured, whether this EHC will be continued even after the reconfiguration, if it works or doesn't work, like that. The details would be configured related to Ethernet compression. Okay, now, so we have completed the second part in it. Third part, user data compression. User data compression means basically application payload compression, application data compression. Normally applications will compress their data, but not always. Sometimes they may not. For example, at WhatsApp, etc., these application level settings, you can choose whether you want your data to be sent compressed or not compressed. You can choose those things. But because if you set it to compressed, WhatsApp messages will be compressed by WhatsApp application itself, And radio network doesn't need to worry about it. It can send as it is because it knows that already the user data or application data is already compressed. It is in the best possible size without having to consume extra bandwidth. But what if user wanted to send their data uncompressed? They have set the application settings like that, or they developed the applications without any compression, decompression. Now, earlier they did not care about it, but more and more applications that are being developed in the world and applications are not having any compression techniques being used. 3GPP saw an opportunity there. They thought that, hey, without we telling this to the applications, why can't we compress it so that we can save the radio resources here? And we can build the subscribers on the basis of the amount of data that they are generating on their applications, because your billing will be done on the basis of IP packet size. In your IP packet size, application size will be as it is. Application data size, if it is 1000 bytes, it will be considered as 1000 bytes. Plus IP header is 20 bytes, it will be 1020 bytes will be built against your head. But at radio level, at PDCP level, we can compress it, and we can compress it and send it from the mobile to Gnode B. So we can save the radio resources there, because we are seeing an opportunity to compress it. So what happens? So you take the application data, you don't bother about the other layers, whether they are present or not. You are compressing the application data itself, the payload itself. Here it is not, concentration is not about other layers. You can observe the kind of thing, like totally your PDCP kind of targeting everything, not only the higher layer protocol layers, but plus application data as well. They kind of doing it overall compression. You wanted to compress each and everything, but doing it separately, not in a combined way. One layer is being done at one level. So PDCP parameters are user data compression implemented in release 17, the latest release finalized by 3GPP. So again, continued UDC operation, and they kind of create a standard dictionary. What is the meaning of dictionary? Whenever you have to compress the data, you have to identify the ones and zeros patterns that are getting repeated. For every pattern, they will kind of give a code or a dictionary code between the sender and the receiver. For example, there is 1000 bytes of data that is getting repeated multiple times in your data. So you kind of create a code for it. You kind of create a standard dictionary code for it. So what happens? Every time that same thing is repeated, you send that code instead of sending the actual data. But here we are talking about the standard dictionaries related to standard protocols. Like for example, SIP. If we are using SIP protocol, SIP or SDP protocols, typically, SIP and SDP protocols are typically huge because SIP works on something called as text-based protocol mechanisms SIP uses. Typically, text-based protocols are very heavy, like HTTP protocol or SIP. Their sizes would be very heavy. If SIP data is not getting compressed, we use a standard SIP dictionary between the sending compression algorithm and receiving compression algorithm. We use the dictionary. So what does this dictionary do? This dictionary kind of create codes for each and everything. For example, in SIP, we'll have a lot of entries like to address, from address, and so on. For each and everything, there will be some kind of little codes created, and these codes are standard codes. These are already standardized, and once that particular software is kept in Gnode B and as well as the mobile, they can use that standard dictionary, standard SIP dictionary. By using that, they will start kind of compressing the application data by using those standard codes. On top of these standard dictionaries, operator also can create the dictionaries to save even more. So these operator created dictionaries are operator choice. So operator can purchase the third party developed dictionaries, and they can use them. So yeah, basically at the time of operation, you can send this information to the subscriber. By using that, you can kind of start compressing everything, compressing these application payloads. Various other factors also configured like buffer size, dictionaries, and etc. This continued the UDC is the same. After the reconfiguration, whether the UDC should continue or should reset and continue, it tells about that. But again, I've not been asked to cover this, but I've covered it anyway uh, as part of. I wanted to give you at least high level information on what is present in each and every protocol. All right. Now that leads us into the next topic. That is the security mechanisms that are in place for PDCP. If you remember, I've done the segregation. So what was the segregation? PDCP is doing totally three blocks of things: compression, decompression, security mechanism, data transfer and management. Now, the second one we are looking at is security mechanism. So what happens? Anything happens there? The first one in the security mechanism is integrity protection. From higher layer, we receive a message. First, we are studying the integrity protection and verification for SRBs. SRBs means signaling radio bearers. You have to kind of consider that message is coming from RRC. It's for signaling message. Because SRB represents signaling radio bearer, which gets the traffic from RRC protocol, L3 layer RRC. Once the message comes in, the algorithm which is already configured with various details, like RRC integrity key, there is something called as bearer ID, radio bearer ID, in which direction this algorithm is working, and there is some running count value. Count value keep on incrementing for every message that we send. By using all these, there is a question. We could have placed it below MAC. It would have compressed. Yeah, that's a good question. Question is good. Doesn't mean the answer is good. The question is this: why can't we place this compressor before MAC layer so that we can even compress MAC header, RLC header, PDCP header also? Anyone? Any answers? Anyone? I want answers. Participation. Come on, guys. The question is not related to integrity, related to the previous compression thing. Why can't we place that compressor before MAC layer, below MAC layer, so that we can compress even MAC header, RLC header, PDCP header also, including all only IP header instead of only IP headers? Why is that? Why we have not kept there? Is what asked by Gautam. What do you think is the reason? Anyone participating?
So there is a lots of deconfiguration and retransmission and harm mechanism.
Retransmissions don't a problem for compression decompression. If sending side compresses it, receiving anyway decompress it. After decompressing, we do the retransmissions. That's not an issue. There is more dynamic info in lower layers. Yeah, that's one good point. More dynamic info in lower layers because it is live information, headers are kept on getting changed. But even then we can do compression. Number of parameters changing dynamically will be large. Yeah, that's the same thing. Both Soumyadeep and Rahul answered are the same, similar. Dynamic information is high. And one more reason, not only dynamic information is high, as what their headers are completely to deal with live traffic, live parameters. Second reason is these protocols are designed by 3GPP. They already made sure that these headers are the maximum compactable size. So they can't be compacted anymore. And most of the times the headers are very, very small. For example, if you take RLC header, Sometimes we use only 2 byte header. Even if you compress 2 bytes header, you will get only 2 bytes. There won't be much compression. Maybe if you can save, you save 1 bit or 2 bits. But the problem is, as the header sizes need to be byte aligned, 2 bytes, if you make it 1.5 byte also is useless because you need to again add another 4 bits in order to byte alignment. As only byte aligned data goes through the physical layer, and as they have decided to do that anyway. So, as the headers are very small and that they are very dynamic, your compression is very low. Even if you save, we will be saving in bits, not in bytes, because the total header itself is in bits or few bytes. So they thought that it is waste of time and effort. Got it? All right. Good guys have participated. Thank you. Okay. So there are a lot of algorithm parameters that are coming up here, kind of going as the input. This NI algorithm stands for, uh, integrity algorithm. What this does is that it is going to calculate something called as MAC-I by taking this message as the input and all these parameters as the input. And when you are sending this message from the sending system to receiving system, you send message plus MAC-I. This MAC-I will be added as a PDCP header. In the PDCP header part, it would be added. So what is the advantage that you get? On the receiving side, you have received the message. The same algorithm and the same parameter values are available also on the receiving entity. So it kinds of put aside this MAC-I that is received, and this algorithm will try to calculate the MAC-I independently on its own. This guy. Now, this MAC-I and this guy's MAC-I, both the MAC-Is must be equal. The received MAC-I must be equal to the calculated MAC-I on the receiving side. Then we will consider the verification is successful. You send the message to the higher layers by concluding that this message is not generated by any hacker or third-party attacker, or we say man in the middle. So this is generated by a proper genuine guy. How do you know that? Because this MAC-I could be generated with accurate value only by the sender, because all these parameter values, the live parameter values, are only known to the sender. Middle guys, at least they don't know at least one. For example, they don't know this integrity key, the hackers in the middle. That would be available only in the mobile and GNodeB, this integrity key. Middle guys will never know that. What is the key that we have to use to calculate this MAC-I? So even if a third party guy wanted to bluff the entity by sending a wrong message with a wrong MAC-I, it will be busted. Once the MAC-I is received, the MAC-I is not matching with the MAC-I code that you are calculating on your own. Immediately, the receiving entity will recognize that it is an integrity failure. I will report to the higher layers, and we have to go for a reset. Higher layer will reset everything. We do the reconfiguration, including PDCP reconfiguration, by assuming that somebody is trying to attack us, and we'll kind of reset everything and go for next level protection. Now all these parameters are maintained on both on the sending entity and the receiving entity. So this RRC integrity is a 128-bit integrity key. It is calculated by the higher layers and provided to PDCP layer. The higher layer is talking about NAS layer. At the time of NAS, we'll study how NAS layer gets this. But in mobile equipment, it is the NAS layer that provides this integrity key. In the GNodeB, it is provided by, it is provided by an NGAP software, NGAP protocol. Higher layers will provide it. You simply have to use it. PDCP would be simply using it. It won't be doing the stuff on its own. This bearer number is a 5-bit number. that is configured at the time of setting up the PDCP. What is the radio bearer number? We already learned that one PDCP is associated with one radio bearer. So every radio bearer will have a number associated with it. That number goes in as one of the input into this mathematical algorithm to compute this MAC-I. Direction represents either uplink or downlink. Count is a number that keeps on incrementing along with your sequence number. A small part of the count is what we call as a sequence number in PDCP. Count typically will be 32 bits. In that, a partial part of it is what we use as sequence number. The entire count value we don't exchange. Idea is, if you send the entire count value, the middle attackers may try to find it out because they can read the PDCP headers, which are not encrypted. Only message is getting compressed. Message is getting integrity protected or compressed. The headers won't be integrity protected or compressed. So middle guys can read the sequence number. From that sequence number, you may not be able to exactly guess the count value because it's only partial part of it. What is that partial part? Anyway, at the time of learning the PDCP related internal in deeper details, you will understand it. It is called as the most significant part will be left out. Only least significant part of the count value is going to be used as the sequence number. You will understand that while you upgrade yourself to that. But if count is 32, maybe if the sequence number is 12 bits, the least significant bits of the count, the first 12 bits, would be used as sequence number of the count. But count is 32 bits, that is locally maintained. Remaining 20 bits would be locally maintained out of 32 bits. That won't be exchanged on the air for protection purposes. So this is for SRBs. Same way for DRBs as well. Data radio bearers also. Message packet comes from the higher layer. We send that through a mathematical algorithm which takes the other inputs and generate the MAC-I and send. Only if the MAC-I is successfully verified, you will consider the integrity verification is successful. Otherwise, we consider that as a failure. And again, this integrity protection is also done by algorithms. PDCP is just going to host these algorithms, that's all. PDCP software, protocol software is not doing it. So there is algorithm software. Typically, these algorithms would be developed by someone else. Even if your company is developing PDCP software, that someone else developed algorithm, you take it and you host it. You just integrate it with your software. Sometimes you may develop it on your own. It depends on if you wanted to achieve effectiveness, you want to develop the same algorithm effectively, you can do that. But these algorithms are already developed ones normally. These integrity protection algorithms or any security algorithms that we are using here. So RRC does the configuration during the radio bearer setup. It configures the SRB identity that would be used as one of the input. Or in case of DRBs, DRB identity. But during security configuration, it kind of tells you which algorithm you have to use. So there are NIA 0, NIA 1, NIA 2, NIA 3, 4 algorithms are there. NIA 0 is kind of no algorithm, no integrity protection. It is basically equal to null integrity protection, not doing it. But if it is configured to NIA 1 or 2 or 3, by using which algorithm we are performing this job of calculating the MAC-I, which integrity protection algorithm we are using. It all are interlinked basically. This is the ASN.1 code. You don't have to worry, you'll learn that anyway. What key to use? There can be multiple keys. One is called as a master key, secondary key, which we call it as K integrity key. So that one, there can be a master one key, there can be a secondary key. Which key is getting enabled? That also kind of will be told to you. And what does PDCP need to do? For signaling messages, PDCP attaches 4 reserved bits in the header. And there is a sequence number which is 12 bits, fixed size. And whatever the MAC-I it has calculated by sending this data portion into the algorithm, that MAC-I it will include as the tile, not as the header, but as the tile. But ultimately that will be considered as part of PDCP header. You can see the color. So this is coming from RRC. For that, you are calculating MAC-I. But if this is for SRBs, signaling radio bearers, for RRC messages, sequence number would be added for every uh, SDU that comes from the higher layer RRC. There will be a separate sequence number. If RRC sends 10 packets, there will be sequence numbers ranging from 0 to 9. But for every PDCP PDU, you have to attach MAC-I by sending this data through the integrity protection algorithm process to calculate that MAC-I. Even for data entities, we call it as DRBs. You still use this, but PDCP sequence number, there is two possibilities: 12 bits or, in this case, it is going to be 20 bits. 16 plus 4, 20 bits. One of the two sizes would be configured. But in case of data or DRBs, because DRBs are having an additional task called as compression decompression, which is not applicable for data coming from RRC. So RRC doesn't require to have D by C bit, because for RRC messages, we only take the data from higher layers, SDUs, and we construct a PDU. Now, there are no control packets applicable for signaling radio bearers. No control packets needed. But for the data, we require the D by C bit, because we already learned that data can go through compression algorithms, and compression algorithm related interspersed feedback packets might be there, either ROHC feedback packet or EHC feedback packet or UDC feedback packet. So to send that feedback packet, those are status reports. They are called as, to send those things, those compression decompression related statuses, you need to segregate the higher layer data that is coming in as data. So D by C bit will be set to 1 when you are taking the higher layer SDU and attaching these details. But if you are constructing those feedbacks, ROHC feedback or EHC feedback or whatever, that time you have to set this D by C bit set to 0, which represents control. So the receiving PDCP understands that it is not containing any higher layer SDU. It is the PDCP to PDCP information. And it kind of opens it and see what is there inside by finding out what kind of control PDU it is. Is it what, if it is a feedback packet, what kind of feedback? Is it user data compression feedback or EHC compression feedback or ROHC compression feedback? You can further find it out based on the control PDU type. There is another 3 bits present there, but these 3 bits in this particular position are reserved. Header design is completely different for data parts and control parts. For control parts, after D by C bits, 3 bits are reserved. Your PDCP sequence number followed by higher layer SDU, followed by the MAC-I you are calculating. Size can be different, PDCP sequence number size, depending on what size RRC is configuring. Again, what should be the size that must be configurable? Should we use 12 bits or should we use 20 bits? That again depends on application speed. And if application is producing large sized packets, only few of them, or very small sized packets, a large amount of them. If very large number of packets are getting generated, you have to use bigger sequence number size so that you have enough range available to store them into your buffer with different sequence numbers, because sequence numbers cannot be repeated in your buffer, in your transmission buffer itself. So again, it depends on the application characteristic, application speed, and how the application is operating. Now this is integrity protection. And the second security mechanism that we have is a ciphering and deciphering mechanism. Integrity means calculating a MAC-I to validate message is accurate or not. But ciphering means encrypting, converting your data into secret format. By using similar keys, we have a KRRC encryption key, bearer, direction, and count. This time we are using encryption algorithm. EA stands for encryption algorithm. N is NR. NR encryption algorithm. So by using the encryption algorithm, you're kind of encrypting the message. You are not sending it as it is in the same format. So you're providing protection to that message. Middle guys won't be able to decrypt it because they don't know the key, or they don't know the direction or the bearer number or the count values. These are all, most of them are secret, only known to the mobile and GNODB. So on the sending side, we perform the encryption. On the receiving side, if you feed the same values to the algorithm, the receiving algorithm will decrypt it and get back your original message out. So this ciphering and deciphering not only works for the signaling messages uh, for RRC, because we are using RRC encryption key here. Now we can use user plane encryption key and encrypt even user data also, the IP packet that is arriving from higher layers, or Ethernet packet that is arriving from higher layers, depending on whether we are using private IP network, private 5G networks, or public 5G network. That will be encrypted, and that encrypted message is what we are going to send to the other entity. On the receiving side, it would be decrypted. PDCP is just hosting the algorithm, and all these parameters, it kind of, some of them are live parameters that PDCP need to maintain and provide that information live to the algorithm whenever compression or decompression need to take place. Or PDCP for these encryption keys, it need to listen to higher layer protocols. When higher layer protocols are configuring them, you get those values and use it for your providing it as the input to this algorithm. Again, the logic is you have the higher layer, which is providing you some configuration. So PDCP listens that configuration details at the time of setting up and kind of provides this information to these algorithms. In this case, encryption and decryption algorithms. Encryption on the sending side, decryption on the receiving side. So even related to this ciphering and deciphering also, um, the radio bearer configuration can be done during the radio bearer configuration. Setting up the radio bearer, RRC tells the PDCP, hey, for this particular SRB identity, you are going to use so-and-so security algorithm. So either NEA0 or NEA1 or NEA2, one of these algorithms. Again, which key should be used while encryption and decryption. Again, the same ways for DRB identity also, it will be, the security algorithms will be configured. They can be separate. We can choose one algorithm for SRBs and some other algorithm for DRBs. But these algorithm softwares are present, and mobile kind of conveys this during its capability information reporting to the network. It tells what algorithms it supports, what encryption algorithms it supports, what integrity algorithms it supports, what compression algorithms it supports. Everything it conveys to the network. Based on that information only, network will suggest among them which one is the best one, yeah, under the current circumstances, operating conditions. So what happens to your data Then we need to understand even that order as well. Why? Anyone? Why after the packet ordering we are performing decompression? What if you perform before that? What is the problem? That's the simple question. Simple as that. Come on, guys. I need participation. One answer we got, but before I tell you that, others, at least I'm expecting 3, 4 answers. Guys, try at least, please. It was complained to me that participation is low and you're not making it any good. Come on, you can do better. Only one answer so far. Okay. Get satisfied with one answer. Fine. The packets, when they are compressed or they're analyzed one after the other in a sequential order. When they are getting decompressed, the meaning is headers are being re-added on the receiving side. They must be decompressed in the same order as well. Reason is, if you take 3 packets, if you take the first packet, the serial number is 5 in the IP header. In the second packet, the serial number sequence number is 6. Third packet sequence number is 7. This is placed into PDCP PDU number 1. This is placed into PDCP PDU number 2. This is placed into PDCP PDU number 3. In one, if you received 1 and 3 and 2 next, this order you have received, if you try to decompress the same way without doing the reordering of them, what will happen now? For this, the sequence number is correctly reconstructed, but for this packet, the sequence number would be, for the second packet, the sequence number would be put as 6 instead of 7, because this order is changed. So when the packets are out of order, the header decompression doesn't work, because on the sending side, header compression is done by analyzing packet after the packet. What is the difference between the previous packet fields and these packet fields? Again, what is the difference between the previous one and this one? So there is kind of a linking, it's kind of a chain. One chaining order is there. If you break that order, if you, without worrying about the reordering, if you directly try to decompress them, it doesn't work. Your decompression fails because the chain is broken. You are trying to decompress the 7th packet from 5th packet. There is no linking between those fields. The increment is not consistent. Increment will be 2, not 1. So that fails. So that is why first you perform duplicate removing and discarding of the things required, and then after completing successful reordering, then only you go for decompression. Once you are sure that all the sequence number packets are arranged correctly, then you do the decompression. Now the success rate of the decompression would be high. Okay, now where are we? in our overall aspect. Now, the thing that is left out is the data transfer and management. What about this data transfer and management? What happens as part of it? Let us quickly complete that as well. First one as part of it is SDU discard. Now, what happens as part of it? You get the data from the higher layers, which we call as SDUs. PDCPs consider them as SDUs, and RRC at the time of bringing up this radio bearer set up a discard timer for it, for this SDU to be dispatched, how much time you have. This would be set up on the basis of applications delay tolerance. This discard timer would be set up. This discard timer kind of play a role in other things also, other things that we have discussed so far. This kind of giving a hint that how much time the packet can be in your buffer before sending it out. Now, what should happen once this discard timer is expired? You should not transmit that again. You should discard it. Even after the discard timer expired, if the SDU is not dispatched because of the you are not getting the resources allocated by the MAC layer, so you kind of drop it. Doesn't matter whether the SDU that is coming from the higher layer is still in the SDU format in the PDCP layer, or is it converted into PDCP PDU, or is it sent to RLC layer already in the form of RLC SDU. Even if it is sent to RLC layer in the RLC SDU, once the discard timer is expired, PDCP hurry burry go and tells the RLC that, hey man, for the PDCP, for the SDU number 15 I have sent you, the timer is expired. Please don't consider it in your buffer. Please discard it. Don't give it to MAC layer. MAC took too much time. If it is still waiting in your buffer, remove it. Normally, why this discard timer is configured? Normally works for live traffic. Live traffic has got some amount of time, which we call it as the total delay tolerance of that application, which we learn it in the QoS classes. So based on the delay tolerance of that application, you say that, hey, after this much time, it is waste of time and effort to send it. If you send it unnecessarily, we waste the radio resources. Even if by sending it to the other side, we are not achieving anything. It won't anyway be played at the receiving side. Receiving application server might even drop it, even after we put this much effort and send it. So if it is too much delayed on the sending side itself, dropping it on the sending side itself makes sense instead of sending it and getting it dropped on the receiving side by wasting the bandwidth. So that's the idea behind it. So RFC configures this discard timer for the packet to be dropped, and it works in two layers: PDCP level, RLC level. Even if the packet is already sent to RLC, also it will be discarded. But if RLC already sent it to MAC layer, then there is nothing that you could do. That means it's already sent out. No, you can't discard it now. Because MAC always, whatever the data that it gets from the RLC, immediately it dispatches by forming a transport block. It won't keep it waiting in the buffer. But PDCP and RLC, they are kind of waiting it, making it waiting in the buffer. PDCP, while it is processing the packets, it will be storing it in the buffer. Because it will have to process these packets one by one in an order, doing header decompression, header compression, doing the integrity protection, ciphering one by one. So while they are processing, getting converted from SDU to PDU, they are working out in the order. While they are in that working order itself, discard timer expired. So for each SDU, there is a separate discard timer. For example, your application delay tolerance is given as 300 milliseconds. Now the discard timer is set to 300 milliseconds. Now for every SDU, the discard value is the same, 300 milliseconds. Is it going within the 300 milliseconds or not? If it goes out, well, very good. Otherwise, discard. Kind of have to work with every SDU's discard timer separately. So it is going to be a little difficult software when you are developing it, because you need to maintain a timer for each one, each SDU. So it can be set based on the delay tolerance of the application, starting from 10 milliseconds all the way up to 1500 milliseconds. This kind of internally drives the RLC logic and RLC AM mode retransmission buffers and retransmissions and pole timers and so on. A lot of things can be derived from it. So when I said the factors, all these things will factor in while deciding those values at that configuration, at RRC level configuration. Okay, now the last concept in the PDCP. Uh, PDCP is allowed to send something called as a status report every now and then, especially during re-establishments. We have a status report already learned in RLC. Why the hell we are discussing about a status report once again? What is this status report required? Why do we need this? Typically, it would be working only for DRBs, not working for SRBs. And network will tell you with configuration, the status report is required or not required. First of all, what is the status report? Why do we need it? What kind of conditions in which we need the status report? So let us discuss that by taking an example so that we'll get the clarity. For this example, we are considering mobile equipment, source G-Node B and target G-Node B, three components. UE, source G-Node B, target G-Node B. UE is kind of requesting source G-Node B that, hey, I want a handover by sending a measurement report at RRC. Source G-Node B communicating with the target and requesting for the handover, for which target accepted. Source tells the mobile equipment to get out by issuing the corresponding command, telling him that it's the time for you to get out from, go away from my network. UE gets out, leaves the source G-Node B cell, syncs with the target G-Node B cell, and reports to target G-Node B that I have arrived by sending RRC reconfiguration complete. So this is a simple, at a very, very high level, and handover scenario by involving XN interface between two G-Node Bs, the primary messages that are involved. Remember, we already have studied X2 interface at MAC level. There we looked for a different thing. Here we are looking for a different thing. We'll again study X2 handover once, two or three more times. Every time we will be looking for different different other details. Here we are, our concentration is from PDCP and RLC point of view for looking this X2 AP scenario. Okay, let us see. Uh, so we are now expanding the same scenario into a bigger picture. We are bloating in, like you are finding the final details. So UE, source G-Node B, UPF, target G-Node B. UPF have sent 4 IP packets to source G-Node B by using GTPU protocol on the NGU interface. Source G-Node B numbered these IP packets in PDCP as 0123 because you use a sequence number for each IP packet. You pack each IP packet into one PDCP PDU. You have 0123. You have RLC numbers also starts from 0 because each guy is having their own numbers. PDCP is having its own numbers, RLC is having its own numbers. They need not be consistent. RLC numbers can be increasing more because it can perform segmentation. Each PDCP packet can be divided into 2 units at RLC level. It's possible because when MAC is requesting for smaller sizes during scheduling, so RLC can kind of do the segmentation of the data. Possible. Okay. Now we are exactly seeing that. The 08th PDCP PDU is getting segmented into 2 RLC PDUs and getting transmitted to the UE in the first 10. Why? Because MAC demanded. MAC said, hey, you can't carry your entire RLC PDU, which is containing a PDCP PDU inside as a single thing. You have to dismantle into 2 pieces and send me one by one. MAC demanded. Yesterday we studied all that in RLC. Now what does UE do? Happily takes it, reconstruct the PDCP PDU number 0, and it can kind of send it to higher layer also, no problem. Now, meanwhile, mobile sent a measurement report asking the source G-Node B, I want a handover. Source G-Node B goes and talks to target G-Node B. Hey, my guy want a handover. Can you please arrange it? While this handover request is being considered by the target, this operation is continuing and the downlink further downlink transmission is going on. Source Gnode B is sending second PDCP PDU, which is in sequence number 1, dividing it into 3 RLC PDUs, sent it out. And the third PDCP PDU number is 2, that is sent as it is in 1 RLC PDU. So totally 4 RLC PDUs have been dispatched by carrying 2 PDCP PDUs inside, or 2 SDUs inside. Again, MAC demanding multiple TTIs, we are transmitting them. Meanwhile, what happens? The third RLC PDU is missing. We are considering a failure scenario. It's gone. Only 245 received. But UE point of view, the first one is not completely received. One partial middle one part is missing. So it cannot reconstruct. SO offset will be clearly telling him that uh, this is a partial one, this is a partial one. Middle one is missing. With the help of the RLC level header, it find out. But it finds out that this is a full one. It might have constructed the PDCP PDU perfectly, but RLC point of view, 3 is missing. It's kind of not constructed. Uh, 3 is not received. 1 cannot be reconstructed now. PDCP PDU 1 cannot be reconstructed at this stage. Meanwhile, handover accepted by the target Gnode B. Target Gnode B is before the handover is triggered, somehow the mobile equipment's RLC is sending a RLC level status report saying that, hey, man, I next sequence number I'm expecting is 6, but tell you what, 3 is missing. I did not receive the third PDCP PDU, third RLC PDU. In that, one PDCP segment is present. If without that, I could not reconstruct that first packet. Can you please retransmit? Mobile is asking source Gnode. Luckily, we sent a status report at RLC level. Okay, now what does the source Gnode do? Anyhow, it will come to a conclusion. Okay, 0 and 2 are kind of successful, but 3 need to be retransmitted. If at all at RLC level, if I have to continue, it is going to be from 6 onwards, but only if the mobile is continuing in this present cell. Meanwhile, handover has been accepted. Source Gnode decided to go for a handover for the subscriber. It tells the mobile equipment to get out from its present cell by sending this RRC reconfiguration request. Tell the mobile to get out. Hey, get out of my cell. Go to the target Gnode B cell as per your request sent by the measurement report. You told me that my cell is not good, that cell is good. Go there. Now, mobile need to kind of go there. It need to sync up and go there. But meanwhile, what the source source Gnode B does, it kind of came to this conclusion based on what's going on right now. And it tells the target Gnode B that, hey man, listen here carefully. In the PDCP PDUs like 0, 1 to 3, I have kind of successfully transmitted 0 to the mobile. Up to that, I have clarity. But 1 is kind of failed. 1 never gone to the mobile. 2 is 2 is sent to the mobile. I kind of know that based on the status report. Mobile would be able to reconstruct 2, not an issue. 3, I never source Gnode B sends to target Gnode B, explaining out of the 4 PDCP PDUs, are there corresponding SDUs present inside it? How many are successfully sent to the mobile? How many are not? It is kind of sending a report to target Gnode B, giving a hint to target Gnode B that you need to continue from here. You have to take over from this particular situation onwards when some mobile equipment comes into your network. And what am I doing? Because I have received these PDUs from the UPF for these numbers, I'm sending you that pending packets. Pending packets 1 and 3. 1 failed one, 3 is never attempted one. I'm sending those 2 things to you with an end marker reporting you that this is the last one. These are the third one is the last one. By using the GTPU protocol, source Gnode B dispatches the pending packets which are not yet dispatched to the mobile. It sends to the target Gnode B. Now, mobile target Gnode B estimates the situation. Okay, once the mobile comes in, I need to send 1 and 3. But RLC kind of gets reset to 0, sequence number 0. Now I keep waiting for the mobile to come to my cell. Meanwhile, mobile completes synchronization and it sends RRC reconfiguration complete by performing random access procedure. As message 3, it sends this message to target Gnode B. Target Gnode B detects this handover arrival of the subscriber and it fatafat makes a decision. Whatever the packets that are not dispatched, it can start sending them to the UE by packing them into RLC PDUs. But RLC sequence numbers will be restarted with 0, 1, 2 because RLC has gone reset. But PDCP PDU numbers are still being continued because they are full packets. Only those full packets are being sent from source Gnode B to target. We are not sending the partial ones on the GTPU. So RLC sequence numbers doesn't matter right now. Ultimately, from that RLC sequence numbers, you can detect whether they are carrying the full ones or not based on the SI information in RLC, the segmentation information. The UE can reconstruct them and it will now have the entire order in place and your RLC sequence numbers continue from 0, 1, 2. So previously, already your RLC sequence numbers are 0, 1, 2, 3, 4, 5. But the numbers are discontinued, but PDCP numbers continued as source Gnode B and target Gnode B are coordinating related to PDCP at higher level, at IP packet level. They are worried about. They are not worried about small pieces of it because this piece is missing. Source Gnode B won't send that piece to target and ask him to retransmit that piece. No, it doesn't work that way because GTPU is used for carrying the entire IP packets inside it in its tunneling mechanism. Okay. Now, RLC is anyway sending the status report here in this particular situation. But why do we need a status report from PDCP level once again? First, we'll see why it is needed. Anyway, further IP packets will continue to target and this situation would kind of continue. But we take the same situation, see another example. Same thing. Everything is same up till here. But now handover has been accepted. Meanwhile, UE did not send the RLC status report to source Gnode B because source Gnode B never requested for the status report, RLC status report by setting the poll bit to 1. So source Gnode B did not know what happened to the RLC PDUs I have sent up to sequence number 5. The present idea from the source Gnode B point of view is, I don't know. I have transmitted 6 of them, 0 to 5, but I am not sure which ones are successfully sent, which ones are not successfully sent, because I did not get any status report. Meanwhile, handover accepted. I am already triggering the handover request to the mobile, telling the mobile equipment to get out. Now, source Gnode B is not aware about what is going on the mobile, how many are successful, how many are not out of the 3 packets sent, out of the 3 PDCP PDU sent, but handover triggered. Now, what does the source Gnode B need to tell the target? Source tells the target that, hey, I'm not sure about any of these packets which are waiting in the PDCP buffer because I need to give guarantee for them. I'm still keeping them in my buffer till I receive the acknowledgement at PDCP level. So nothing. I'm sending all of them to you. You need to retransmit all of them to the mobile equipment once the mobile arrives at your cell. So you send all the pending packets to the target. Once the mobile arrives by completing the handover, target will resend all these things 0, 1, 2, 3, 4 once again, everything. Now, mobile's PDCP 0 and 2 already received. It will kind of identify the duplicates and discard them at the PDCP level because PDCP sequence numbers are still continuing even after the handover. Only RLC sequence numbers got reset. PDCP numbers are continuing. So you can detect that this 0 and 2 are got retransmitted once again by the target G node B. Doesn't matter who retransmitted them, but the retransmitted, yes, they are. You discard it. You won't need to send it to the higher layers. You only send them in the correct order only one time. What is the disadvantage with this problem? What is the problem here? This problem occurred, why the duplicates occurred, why we made the target G node be sent this, all these things once again, because there is no report happened from the mobile to G node B before the handover. RLC report did not occur. RLC status report. Now it is radio wastage, radio resource wastage, because we are duplicating it, because we are not sure what's going on with the mobile. How many received, how many not received, as the status report did not come. Now, to avoid this situation, they have invented PDCP status report. But PDCP status report happens after the handover, not before the handover. So how it works out when PDCP status report is in place? Same situation once again. Same things are missing, same scenario. Again, we are taking source G node. We don't know anything about what's going on because UE never sent the status report. So you don't know how many RLC PDUs have been sent from that, how many PDCP PDUs have been reconstructed. You are not sure about it. Meanwhile, you trigger the handover to the mobile, but you clearly tell the mobile that at the time of triggering the handover, source G node B tells the mobile, hey man, I don't know about what happened on your side related to your status report. Right now, I'm not even interested because I'm triggering a handover. Even if I know I can't do anything much as you are moving away. So better after your handover, you report your PDCP related status situation to the target G node B. You please report it. So source G node B advises UE in this RRC protocol message, RRC reconfiguration request message. But source G node B tells the target G node B that, hey, I am not sure about any of these things, so I'm sending you for the purpose of safe side activity. You might have to resend all of them because I'm not sure what happened on the mobile because I did not receive a status report from the mobile from RLC level at RLC level. So I'm forwarding all the packets by considering them as pending packets in my buffer, PDCP level buffer, because for none of them I have received the status report from RLC. Forwarding, you deal with the user, but I told the user to send a report to you after coming back. So target G node B's present idea is that I need to retransmit all of them. But once mobile arrives with the handover complete, then first thing UE does is it sends a PDCP status report telling G node B that, hey, the first PDCP PDU number I cannot reconstruct. One is missing, but two is received. This one bitmap one will represent that two is received. One is missing, from the missing one onwards, two is received, 3, 4, 5, nothing is received. 000 represents each bit will map to one sequence number. So none of them have been received. Only one is missing, two is received. Of course, 0 is received because you are reporting the first missing sequence number is 1. That means 0 is received. 0 is received, 1 is missing, 2 is received, 3 onwards, nothing is received. Once you send this message, target G node B will kind of update itself. It says that, oh, now out of the 4 packets that are sent by source G node B as the pending ones, I need to retransmit only 1 and 3, or I need to transmit only 1 and 3 because mobile has updated me and told me that 0 and 2 are already received. I don't need to duplicate it. So I would be kind of sending only 1 and 3, and mobile equipment doesn't have to discard anything, and it can rearrange the things in the correct order and send it to higher layers as it reconstructed the PDCP PDUs from my RLC PDU constructions. So you are saving the radio resources here by just reporting this PDCP status report. And further IP packets will continue. So the basic idea is here the coordination need to be created at PDCP sequence number level among three components. Those three components are mobile, source gnode B, and target gnode B. So that coordination happens not at RLC sequence number, but at PDCP level sequence number, where for the complete SDUs that are pending in the buffer, for them you coordinate. Pending ones would be forwarded. But this mechanism works only if the PDCP is working with an RLC entity operating in AM mode. If PDCP is working with a RLC entity operating in UM mode, this won't be done. There is no packet forwarding, there is no status reportings, nothing. If it is working in UM mode, it is working in AM mode. If a PDCP is operating with UM mode, we call it a seamless handover with technical wording. If the PDCP is operating with the RLC AM mode entity, PDCP works the way that I'm showing here. There will be status reports and everything, full coordination. You won't be missing anything at all. This is called as a lossless handover. In lossless handover mode, you make sure that even during handovers, you won't be missing any packets. But that won't be the case for mode, because for mode, you kind of carry the live traffic. You don't have the time during the handover to coordinate and send the packets from one gnode B to other gnode B to send it, because the application is not that much delay tolerant. So your time is already lost during the handover. So that kind of will be discarded already based on the discard timer. You won't have the time to forward it to the other gnode B and send it. So the fourth type of control PDU with which we have finished PDCP, device bit will be set to 0, and 000 would be is the value of PDU type, which represents PDCP status report that is sent during after the handover, after the reconfiguration of the lower layers. First, you report first missing sequence, first missing count value, 32-bit count value we put. From the first missing count value, how many are missing? Bitmap. Each bit will represent one. For the example, if the first missing sequence number is count value is 87, this bit will represent the status for 88th bit or 88th sequence number, 89, 90, like that. For one bit will represent the status of one PDU. So if this 88 bit is set to 0, it is missing. 89 bit is set to 1, it is received. 90th bit set to 0, missing. Next 1 received, 1 received, 1 received, 0 missing, 1 received, like that. Starting from the first missing one. That they kind of designed it like that. Bitmap mode. But ultimately, a status report will give complete clarity about what's going on. So this is applicable only for AMDRBs, not for UM. Of course, format is there in UM also, like because other things are needed, control element format, like in ROHC feedback will be there for UM, also AM. But this status reporting only applicable for AM. Okay. So any questions with this particular part? So have you all understood this thing? Any questions in this? Now you understood why RLC would be reconfigured uh, during the handover, because RLC will be containing the partial pieces for which we never send the status report from source to target. They won't coordinate on that. So that's why they decided to discontinue those numbers and throw the packets into dustbin. But anyway, PDCP will take care of the reliability of the packets. PDCP keep the SDUs in its buffer till it gets the acknowledgement, especially the PDCP which is operating along with RLC AM mode entity will work that way. So it maintains the copies of the SDUs till it gets the acknowledgement from RLC level. Either at RLC level or after the handover, you receive the status report from the other entity, from the other PDCP guy, the the mobile equipment in this particular case. Till that time, you keep maintaining those packets in your buffer, but works only for delay tolerant applications, not works with you know non-delay tolerant applications, which you normally work in RLC with the UM mode entity. Okay, there is uplink part also I have to show, but we don't have time. We already overshot by half an hour and plus more. We stop here for today on this subject. We take a break of about 10